All right, pre-calc, here we are with 3.2, logarithmic functions and their graphs. Okay, we just got done looking at exponentials, and every exponential function a to the x would pass the horizontal line test and therefore would have to have an inverse. And this inverse is called the logarithmic function with base a. Okay, so for all x's greater than 0 and a's greater than 0 and a not equal to 1, we have y equals log base a of x, if and only if x would equal a to the y power. Alright, so when you're flip-flopping these back and forth between exponential form and logarithmic form, just know that they're inverses. One undoes the other one. Okay, so you're kind of converting back and forth there. And when I'm doing a log, I want to put it so the single thing is over here and the log is on the right. Because just a little mental trick that I do is I read it out loud in my head to myself. Here I'll read, y is the power of a that gives me x. So then that makes it easier to translate it into a exponential. Y is the power of a that gives me x. Later on down here we're talking about 2 and being 3, 2 and 3 and 9. So 9 is 3 squared. 2 is the power of 3 that gives me 9. So 2 equals log base 3 of 9. 2 is the power of 3 that would equal 9. So then if you see a blank, like if it just gives it to you like this and you're trying to fill in the blank, think what is the power of 3 that gives me 9? And you come up with 2, or 3 to the x equals 9, and then you can kind of think about it like that. Okay, just what we just got done talking about here, y equals log base a of x, and x equals a to the y are equivalent. The first equation is in log form, the second is exponential form. We just talked about 2 equals log base 3 of 9, can be rewritten as 9 equals 3 to the second, or 3 to the second equals 9. 5 to the third equals 125, so 3 is the power of 5 that would give me 125, and again, that's why I would kind of go the other way around. 3 equals log base 5 of 125. That's just how I say it, how it works in my brain. Again, if you had a different teacher last year, I believe we talked about these last year just a little bit in Algebra 2, and the way that your teacher presented it to you at that time worked out for you, you can go ahead and keep going on that route. When evaluating logarithms, remember that a logarithm is an exponent. This means that log base a of x is the exponent to which a must be raised to obtain x, kind of what we've been saying before. Log base 2 of 8 is 3 because 3 is the power of 2 that gets me to 8. Okay. Graph these in the same plane and compare. We're going to see that they are inverses and that they would be reflected over the line y equals x, which is an indication that they are inverses of each other. So 2 to the x and log base 2 of x. Let's see if we can remember where that is. Math. Log base. It's like the 10th option or 11th option there. Math, log base 2 of x. Alright, graph. So there's our 2 to the x and there's our log, and you can kind of see there that they would be reflected over the y equals x line, which is an indication that they are inverses. Okay, when graphing, another thing to think about if you ever have to graph these, y equals 2 to the x, so if we put in -1, 2 to the negative half, or 2 to the negative 1 would be a half, 2 to the 0 is 1, and 2 to the first is 2. Alright, when we do the inverse, log base 2 of x, those get flipped, Okay, when you do an inverse, your domain and range get flipped. So these are now my x's, half, and these are now my y's, comma negative 1. 0, 1 would become 1, 0. 1, comma 2 becomes 2, comma 1. The nature of the graph below is typical of functions log base a of x. When a is bigger than 1, they're going to have an x-intercept and a vertical asymptote. Alright, and they will slowly climb after we get above 0. Before 0, climbing very rapidly. After we cross our x-intercept, very slow. Very slowly rising. Okay? So, our domain for those would be x's greater than 0. Range is going to be all real numbers, going forever down, forever up. The up part's pretty slow. X-intercept is going to be 1, comma 0. Just like the other one, the y-intercept was 0, comma 1. Now we're going to have an x-intercept of 1, comma 0. Increasing 1 to 1, meaning it passes the vertical and the horizontal line test there. So it would have an inverse that we just did the unit before. Vertical asymptote at x equals 0, aka the y-axis. It's continuous, and it's a reflection of our exponential form over the line y equals x. And the basic characteristics of the graph f of x equals a to the x are shown below to illustrate the inverse relationship. Alright, so you'll notice that these should all be flip-flopped. The domain is now the range is the domain. Okay, our y-intercept is now our x-intercept. Horizontal asymptote at y equals 0, vertical asymptote at x equals 0. So these two just kind of flip-flopped everything. Alright. Looking at a picture and coming up with an equation. So the dotted one is going to be the standard y equals log base 10. Right? If this is common log, if it just says log and there's no base number, it says log 10. Which is a lot easier to get to on your calculator. Right here next to 7 is log. Boom. Just common log or log base 10. So what do we have here? It's tough to see. It's really small. If I zoom in, I'm not going to be able to see the rest of it. That didn't work. Alright, so it does appear that we just shifted 1 unit to the right. So we're 1 unit to the right. Okay, so we're going to have y equals log of x minus 1. Okay, the shifting in parentheses with the x is going to move it left and right. Okay, this one appears to have moved it 1, 2 up, 2 units up. So y equals log x. And then a plus 2 on the outside is going to move things 2 up. This one appears to be just flipped. Is it slid up at all? Well, let's just see. Our nice point here appears to now be there and over 1. So maybe we're reflected. We're right 1 and up 2. We're vertically reflected. So y equals negative on the outside is going to flip it up and down. Negative, well, we don't even need parentheses around it, just negative log. We said 1 left, so backwards, so that's going to be x plus 1. And then we're still, did we say 2 up? 1, 2 up. So this can be kind of tough to tell because the curves they don't hit very many nice points, so it's kind of tough to find one and track it. but do the best you can with those with looking at the graph and then coming up with the equation. Okay, we talked about e being a special exponential one. It's just it's the same exponential rules. It's just that e is a special number. So it's going to have its own special natural log. The inverse function would be called the natural logarithm function and is denoted by the special symbol ln of x, where the natural log of x, or ln of x. Note the natural log is written without a base. This base is understood to be e. Alright, so if there's log, log, with no number underneath of it, it's just assumed to be a 10. If it's ln with nothing underneath, well, it's going to be e. It's its own thing. Or sometimes you might see it written out log with a little e below it, base e, like this. Okay? The definition above implies the natural log function and the natural exponential function are inverses of each other. Yep, that's true. That's where they came from. They're inverses of each other. And you can see that their graphs are also reflections over the line y equals x. On your calculator, the ln button is right there next to the log button, just down here below it. It's a lowercase ln, not a capital ln. So if you need to find that, that's where it is. Alright guys, that's all we have for 3.2. If you have to do any graphs, you can use your calculator to help you out with those and come up with some nice points. Just a couple nice points per branch there to help out with those. If you have any questions, make sure you're letting us know. Thank you very much. We'll see you in class.